Energy expenditure in animals is essential to the proper function of vital human processes. Like all mammals, humans break down food through a variety of complex chemical reactions. Humans utilize the nutrients that are extracted through digestion to maintain temperature and concentration gradients, and to synthesize, transport, degrade, and replace various molecules that make up body tissue. Calorimetry is the study of heat transfer during a chemical reaction. In the experiment, the combustion of a nut was measured in calories. A calorie is a unit of energy that is estimated in the following experiment by measuring the overall heat change in a container of water as a consequence of the combustion of different nuts.
Because dietary recommendations are constantly changing, quantifying nutritional content of food is extremely important. The data provided by nutritional labels gives people the power to make educated decisions on the food that enter their body to live a healthy lifestyle. This tool is a demonstration of a process that scientists use to measure the caloric content of different foods.
The calorimeter design consisted of a large can and a smaller can holding water. Holes are drilled into the bottom of the large can to facilitate the combustion reaction. Inside the larger can, a cork with a nail and a nut sat at the bottom. A smaller can that contained water hung over top of the cork with enough space for a flame to be produced.
Water was poured into the small can and the mass and temperature were recorded. Then the mass of the nut was recorded and it was placed onto the nail. After lighting the nut with a torch, it was placed inside of the calorimeter device. As the nut burned, the combustion reaction produced a flame that came into contact with the bottom of the water can, which absorbed the thermal energy by conduction. Due to the temperature gradient between the heated can and water, the thermal energy spreads throughout the water by convective heat transfer. Then, as soon as the reaction reached completion, the final temperature of the water was recorded. This change in temperature was used to calculate the quantity of heat transfer.
Once the change in water temperature was found, the equation Q equals mc delta T was used to calculate the amount of heat that the water absorbed. Q is the total heat transfer in joules, m is the mass of the water in grams, Cp is the specific heat of the water in joules per gram degree Celsius, and delta T is the change in temperature of the water in Kelvin. The calculated Q in joules was then converted into units of calories and divided by the mass of the nut in units of grams to find a ratio of calories per gram of the nut. There were some sources of error regarding heat transfer in this design because not all of the heat was transferred into the water. Some was lost to the air surrounding the device, and the soup can was not a perfect conductor of heat and had thermal resistance.
Certain factors such as heat loss to the ambient environment and thermal resistance of the steel cans prevented maximal heat exchanged. Although the measured caloric values were roughly half of the known values on the nutritional labels, they only deviated slightly, which demonstrates the measurements were precise. For future experimentation, the thermal insulation could be improved to minimize heat loss to the ambient environment. Changes in material could also improve the overall heat transfer because steel is a poor conductor of thermal energy. These improvements could significantly improve the overall heat exchange, while also minimizing potential heat losses to the ambient environment.